happens if you add 1 to a number? It gets bigger. We don't directly have the biggerness concept in here, so we could write 1. How much bigger does it get?
By 1 unit.
It's one bigger, it's a successor, right? It's the next thing up, right? So let's prove that. So if you add 1 to a number, or any number at all you can choose, if you take the number and add 1, that is equal to the successor of the number. Yep. I'm just going to be careful with my brackets too, I guess. Those two go together and those go together. I'll often drop those brackets because it kind of implies mathematics. If we're being careful, that would be the case. So adding 1 to the number gives you the successor. This is the universals, we did the universal introduction. A plus SO equals S of A. Line 1, line 2. This is an identity, so we're going to do identity introduction from line 3. Line 3 is going to be a great big block. It's an identity introduction. A plus S0, S of A. I'll leave you to fill in the gaps. And the way I'm doing the easy stuff, this is all from the first, well, this is from the first week of course. This is just a rule for identity that we learned last week. And this is our new stuff up ahead. Okay, so I'll just talk out loud through this. We're adding a number that's not 0. This is rule 4. That's going to be successor of A plus 0. That's the x and the y in that equation. Now, successor of A plus 0, I'm adding a 0, so that's rule 3. And that's going to give me S of open brackets A close bracket, which is really just S of A. So I'm just skipping it straight down and going Q3. Okay, so now we've proved a general rule. Adding 1 to a number gives it successor, which we kind of thought, because that's how I describe successor, but it was just a symbol. We didn't know this was the case. This is a new result. Okay. Let's move on to this more interesting one now. This is a problem. It does not exist, so it's not the case that there is a number that 2 times that number times 2 is equal to 3. Okay, now that's got an existential in it. Let's have an existential first, and then we'll move on to that case. That's what we're aiming for. I'm hoping that this one was okay. If I made a mistake, if there's any questions, other than going on to existentials. Okay. There exists a number such that 2 times that number is equal to 2. It's the simplest case I can think of. Okay. Well, that's what we're trying to prove. This is an existential, so we should be using an existing thing from our proof above. Existential introduction, we use an existing one. But there are no existing ones, so we're going to have to guess wildly with no clue. So maybe 133, maybe 2 million, maybe 17 trillion. Can someone think of a number you want to guess first for this? Sorry? 1? Sure, that's a crazy number. Let's try that. So we're going to use, I'm guessing you're using some sort of developed intuition over 20 years of mathematics, which is how logicians talk. This is what actually has happened, right? You can kind of see. We're going to choose, that's a number here, and I'm going to write out the 2 in normal writing. and we've done existential introduction from 2. So yes, what you use is you use the parallels between this random arbitrary system and your mathematics to pick a number that works. And I think you've picked right. If not, we'll both be embarrassed. So, okay, so now we want to prove this. You can prove this, then there is some number like this, namely 1, the second number we thought of. And this should be reasonably straightforward to prove. Let's just do it a little backwards, because of course these are the same thing. SSO, therefore SSO.SO. It's the same process, all the lines are the same, which is good practice to work backwards and upside down and in a hurricane. One step at a time, we're working backwards. Yes?
Is it just for the example, or we can always reverse it?
Equals is always reversible. Yep. And that's true for these rules here too. That's why I did some of the stuff before, because you can go from here to here if you want to go from here to here. If you've got a 0, you can always replace it with an x times 0. You've got to pick your right x. If you've got a 0, you can replace it by 3 times 0. Why 3? Because you think it might be useful later. You can always go backwards or forwards with all the equals rules. They're always 2 directional rules. And this is just to get you to practice thinking the other way. So let's see. SS0, well, it's the same as SS0 plus 0. 2 is equal to 2 plus 0. And that's the same as SSO plus anything times 0, right? 0 is the same as anything times 0. So let's just stick up like SS0 in there. And now we're going to use Q6. Again, in the opposite direction we've been doing before. So here's Q6. We've got x plus x times y, and that's going to be x, which is this x here, times the successor of y yes.
Doesn't matter which way you prove it?
You mean which order, up or down?
Yeah.
No, which is why we deliberately did it backwards. And the sensible way to do would have been to start at this one and work right to there. But that wasn't nearly as much fun. So you can do it either way. You probably would start this way and go that way. That's what I did in my head when I read it backwards. But sometimes it's easier to start both directions and meet in the middle. Sometimes it's useful to actually be able to work it the other direction. So when you're starting off, start this way and spread it back. But sometimes it'll be useful how to do this as well. So I'm just showing you it is possible to remind you that these rules do work both ways. Yeah. But start off simple. Ice skating backwards after ice skating forwards. It's actually only like 10% harder to ice skate backwards than forwards, I've been told. I can't do either. Can anyone here ice skate well? Anyway, is backwards and forwards kind of about as easy, almost?
It's the same thing.